Hey, welcome back. Today we're looking at functions. This should be a review from Algebra 2. But yeah, if you need catching up, then now's the perfect time. So the whole idea about a function is each input, which is your x values, has only one output, your y values. We're going to be looking at functions and non-functions using different types of parts of mathematics. So one way we could be looking at would be mapping. Now, mapping may or may not be familiar to you, but what it does is it has an input function. Well, not a function, an input and an output. So let's say we put names in here. Gene, Marley, John. And let's say this function is showing what each of these people, their favorite ice cream is. All right, so let's say we have chocolate and mint. All right, so for a function, remember each input has only one output. So let's say Jean likes chocolate, Marty likes mint, and then John also likes mint. This represents a function because each of those people only have one output. They only like one type of ice cream, or that is their favorite type of ice cream. Even though Marley and John both like mint, it's still a function because each of them only has one. All right, for a non-function, then let's say we have the same people. We have in, out, and then this time, let's say we are looking for their favorite genre of music. Okay, so let's say we have hip-hop, we have country, and then we have pop. All right, so let's say Gene likes hip-hop, Marty likes pop, and then let's say John can't decide, so he chooses hip-hop and pop. All right, this is no longer a function because John, that one input, has two separate outputs, so that makes it not a function for this mapping. All right, so always keep in mind when we're talking about functions, just make sure that each input has only one output and you should be okay. Let's take a look at another type. So let's say we have a set. So a function is, for a set, our set is just a bunch of points. So each point has an x and a y. So a function might look like 0, 1, 1, 2, and then 2, 1. So this is a function again. 0 only has an output of 1. 1 only has an output of 2, and 2 only has an output of 1. There's no multiple x's that have different y's. Even though in this one and this one we have the same output, that's fine because both of those are different x's. All right, so for a non-function then, and you might be able to kind of figure out what a non-function might look like here. So let's say we have 0, 1, 1, 3, and then 0, 2. This is, oops, that shouldn't be a comma there. Okay. The reason why this is a non-function is because we have an x here with a y of 1, but then we have an x here with a y of 2. This has two different outputs. It has two different y's for the same x. So that's what a non-function would look like for a set. Equations are a little bit more difficult to identify, but really not. So an equation that's a function would look like y equals pretty much any of the things that you've been studying up until this point. So like x squared plus 1, right? Because no matter what we put in for x, there's only going to be one answer for y, right? If I put in a 1 there, 1 squared plus 1 is going to be 2, right? There's not going to be multiple answers for any of the x's I put in. Now, a non-function, be careful here, and this is a dead giveaway. Anytime we have y to an even power, we're going to have a non-function, and let me explain why. Because if we're trying to solve this for y, we'd square root both sides, right? And we'd we'd have the square and the square root undo each other, so we just have y. But we said that anytime from now on that we take a square root, or any even root for that matter, of a number or a variable, we have to put positive and negative in there. So let's say we had our x was 4. The square root of 4 is 2, but then we have both the positive and negative 2, so this would end up being 2 answers. So this would be positive and negative 2, right? So the positive 2 is one of the answers, the negative 2 is the other answer, so we have more than one output per input of x. So again, when we're looking at equations, look for the ones with the even power on the y, right? This one is okay, it's an even power on the x. That's not going to change the fact that we're only going to have one output per input. Okay, and lastly, we're not going to really get into this today, but we might as well do it since we're talking about functions and non-functions. It's a good place to have it. The vertical line test, it's very wordy, but it's really simple in its execution. So if a vertical line cannot be drawn anywhere on the graph that passes through more than once, it's a function. So let's kind of take a look at this. This would be a function. And then this would be a non-function. All right, so let's see how the vertical line test plays into this. So if we're looking at this function, there's no place I can draw a vertical line here that's going to pass through this graph more than once. There's no place on there, so this is definitely a function. Now, this is a non-function, even though it passes the vertical line test here and here, and all on this side, there's many places in the middle here where it's going to cross through more than once, so that would be an example of a non-function. All right, so let's kind of apply this. Well, we're not going to apply it right now, sorry. From that, the first thing you guys are going to do is do that function or non-function thing. That should be pretty straightforward. One of the important things, though, is we're going to be looking at domain next of a function. So there's two major things that we're going to be looking for when we're looking at domain restrictions. So for the most part, all the functions that we're going to be looking at, the domain for is all real numbers. We could put any x in there and come out with an answer, so we should be good with that. The only problems we come across is if the denominator equals 0. Now, if you guys haven't looked at this before, the reason why we never divide by 0 in math is for this reason. So if I have something like 2 times 3 equals 6, right? We know that's true. We knew that's true from elementary school. But what we also know is that we can rewrite this as a division. So if we rewrite this as a division, then we say that 6 divided by 2 is going to be 3. Right? These are related. They're tied together. And multiplication and division are inverses because of this type of relationship they have. Now, this also works if I did 0 times 2 equals 0, right? We know that anything times 0 is 0, because if we did this in the same way, then we'd say that 0 divided by 2 is equal to 0, right? That makes sense. Anything divided by 2 is 0. 0 things in 2 separate groups. Each of those groups has 0 things. Now, the reason why we can't divide by 0 then is, let's change colors here. So let's say we did, 2 divided by 0 is equal to 0, right? So by the same logic, then 2 has got to be equal to 0 times 0, but that's never ever true, right? 0 times 0 is not 2, so this is not correct. And this is why we can't have a denominator 0, ever. Okay. Now the other one is if the square root is negative, or any even root for that matter. If we have a negative there, then it's not a function. So let's talk about why that is mathematically as well. So let's say that we have the square root of 9. Well, we know the square root of 9, we have two answers, right? We talked about this before. Anytime we square root in Algebra 2 and higher, we have two answers. We have positive and negative 3, because positive 3 times positive 3 is 3. Also, negative 3 times negative 3 is 3. So what it's asking us when we square root is what times itself is the number, in this case 9. right? But the problem is if we have a square root that's negative, there's really no answer to this, right? Because if I have positive 2 times positive 2, well, that ends up being positive 4. If I have negative 2 times negative 2, that still ends up being positive 4. There's no way that we can multiply something by itself, because positive times positive is positive and negative times negative is positive, that we're going to get a negative inside of the square root. So 2 things to be careful of. If square root is negative and if denominator is equal to 0, then we don't have an answer at that part, and therefore it's not part of the domain for our function. All right, so let's look at here. So this one is a polynomial. We don't have any denominators, we don't have any square roots. So for the domain for this, all real numbers. So 99%, well, maybe not 99%, but 95% of your functions will have no domain restriction. It's always going to be all real numbers. The only time we really need to be careful is that if we have a denominator with an x in it, or we have a square root in there. Okay, so let's look at number 2. The top doesn't matter. We could have anything up there other than a square root, and we wouldn't have to worry about it. In this case, we're just looking at the bottom. So we have a denominator here. So we're trying to figure out, when is x squared minus 4, the whole denominator, going to be equal to 0? Well, we can solve this pretty easily algebraically. We can add 4 to both sides of this. And then when we divide, we get x is positive or negative 2. So if I were to plug in positive or negative 2 into this function, the denominator would be 0. So the way we're going to write this then, kind of running out of space, is for the domain, what we can write is 2 different ways. So the first way we're going to write is set notation. X such that, so that line means such that x is not equal to 2 or negative 2. And then close your braces. Right, so I like to write it that way. A lot of times they don't accept that version. So on your standardized test, the second way would be, and it's a little bit longer, let's write it on top because I'll run out of room if not. So from negative infinity, because we pretty much have all real numbers except for two of these points for x, positive and negative 2. So all the way to 2, or negative 2, sorry. I'm going to put a parentheses there. That means it doesn't include the point negative 2, which is important, right? Because if we did include it, that means that we'd be able to plug in a negative 2, and that's not correct. And then u, negative 2 again, all the way till we hit the positive 2, and then u, positive 2 to infinity. So this is another interval notation that we can use. It's probably more widely used than the set notation, but either way you want to do it, I'd say stick with set notation as long as you identify where the restrictions are. Okay, number 3 is a square root type problem. So we said that the square root has got to be not negative, so it's got to be either 0 or positive. So one way we can set this up is we can say that it's greater than or equal to 0, right? That means that it could be 0 or bigger. Right, so let's go ahead and start solving this. So well, actually we don't even need the square root. We just need to worry about what's in the square root. So we can say 4 minus 3 theta is greater than or equal to 0. Let's solve this for theta. We're going to subtract 4. And then we got to divide by negative 3. Be careful, remember from your algebra, that anytime we divide by a negative on both sides or multiply by negative on both sides for our inequalities, that we got to flip the sign. So theta is going to be less than or equal to negative, and negative is a positive, so 4/3. So that means any number that we plug in that's equal to 4/3 or greater or less than 4/3 should be okay. It should give us a positive inside of our square root. So if we want to write this in integral notation, it would be, in set notation, it would be x such that x is less than or equal, oh sorry, not x, we're working with theta here. theta such that theta is less than or equal to 4/3. In the case where we only have above or below the number, like we do here, it's kind of easier to write it in interval notation. So we're just going to say because we're looking at less than 4/3, negative infinity, everything to the left of 4/3 all the way up to positive 4/3. And because it's or equal to, we're going to put a bracket there. Okay, if you're not included, we'd have all parentheses like the top one. So be very careful with it. It's something that you need to practice to get used to, but the more you do it, the easier it gets. Okay, and then the last one, this has two things going on, right? So it has the top radical and it has the bottom. So the bottom is pretty easy. So we know that x minus 5 is not going to be equal to 0. So then we add 5. And you could do this in your head if you want to. Probably x is not equal to 5. Right? Because if we do 5 minus 5, our denominator is 0. We break math. Okay, now on the top one, we know that 3x plus 12 has got to be greater than or equal to 0, because in the radical, we need to have a positive inside the radical. Let's go ahead and solve this algebraically. 3x is greater than or equal to negative 12. Divide by 3. Now be careful here, we're dividing by positive 3 on both sides, not negative 3, so we don't have to flip the sign. Okay, and then let's write this out. So let's do this set notation first. X such that x is greater than or equal to negative 4 and x is not equal to 5. Whoops. And then in interval notation, we're going to go from negative infinity. Oh, sorry. From negative 4 is the least that we could have. And that's or equal to, so we're going to put a bracket there. All the way to 5. But not including 5, right? So there's a parentheses. And then from 5, because anything bigger than that should also be good. So from 5 to positive infinity. So when you're setting up this interval notation, if there's no restrictions on the ends, just make sure that it goes to infinity on the right and negative infinity on the left. The reason why we don't go to negative infinity on this one is because we have the radical and everything's got to be greater than the negative 4. Alright, so whichever way you want to do it, if you want to do set notation is a little bit more intuitive, I think, because if you look at it, it explains pretty much exactly what you're saying, right? So for this one, x such that x is greater than or equal to negative 4. That's exactly what we found here. There's no confusion between what we did mathematically and the notation. And also the x is not equal to 5. That's exactly what we found here. It's pretty straightforward. The interval notation, while it is useful and it's easier to look at in some cases, it's a little bit more complex because there's a gap between what we found mathematically and what we're trying to state here. Yeah, so whichever one you guys want to do, try to eventually get comfortable with both. Okay, and I believe that is it. So good job today. Make sure you take down your notes. Make sure you try to keep up with your work. I know some people might be having trouble at this point, so please show up to class. Please ask questions, even if it's for stuff that was due a little while ago. Yeah, try to keep up. Do not as much as possible. Try to not do anything and then try to complete it all the way at the end of the grading period, because that means that I have to correct a lot of stuff, which is not too bad. I mean, it does stress me out a little bit, but on top of that, it's sometimes people can't meet that deadline. They wait too long and then they're not able to hand their stuff in on time, and that's just, yeah, it's bad for you because you kind of rush through everything. You might not remember things, and then on top of that, I gotta do requests to change grades at some points, which is kind of a headache because I gotta go out to the registrar's office and fill out paperwork and answer questions and stuff like that. It's not good for anybody. So please try to stay on task. I'm not asking that you come in all